Let's go ahead and start with the first thing we want to attack, proving that the derivative of sine is cosine using the definition of derivative. Okay. Here we're going to have to recall what the definition of derivative is. So we're going to look at the derivative of sine of x. It's the limit as h goes to 0, sine x plus h minus sine of x all over h. So that is the definition of derivative. Okay. Now I want to compute this limit. Now the problem here is that we've got these two variables, x and h, and they're all mixed up together. In fact, the x and the h are mixed up together in the argument of the sine function. So I'd like to separate them apart. Do I have any way to rewrite sine of the sum of two angles? Well, this is where our trigonometric identities come in handy. We have a trig identity which says the sine of the sum of two angles can be expressed in terms of the sine and cosine of the individual angles. So it's sine of x, cosine of h, plus cosine of x, sine of h. So that's sine of x plus h written involving the sum angle identity. And then we've got this minus sine of x hanging on the end. And all that's over h. Okay, so we've now split up what was an argument involving both x and h. We've now split them up so that the arguments of any of the trig functions involves only one of the two variables. Since my limit involves h, I'd like to take everything involving an x and push it out front of the limit. Get it out of that limit. The only thing that's changing is h in this case. So take everything involving an x and throw it out of the limit. Get it out front. Okay, so the thing to note here is that, well, there's a sine of x and there's another sine of x. So maybe I should pair those ones together. So if I take the sine of x, one of them was paired with the cosine of h. The other one was just by itself. So if I factor out, that leaves me a -1. There's an h in the bottom. So I've got an h still in the bottom. Then there's this other term here, cos of x sine of h. That involves something involving x, which I'll bring out front. And then it involves other stuff involving h, which is the sine of h over h. And then all of that, we're taking a limit with respect, well, we're taking a limit as h goes to 0. So now I've split everything up. I can take everything involving the x and throw it out front of the limit. So I've got the limit as h goes to 0 of cos of h minus 1 over h. And then I've got that other piece, which involves the cosine of x, and the limit as h goes to 0 of sine of h over h. Okay, now we've made it somewhere. What we're looking at here is we've reduced the entire problem of computing the derivative of sine of x to the question of what is the value of these two limits. What is the value of these two limits? Turns out that this limit is 1. And it turns out that this limit is 0. And we will verify these. So don't worry, we will verify these below. That's the next thing we're going to do. We're going to verify these. That leaves me with the cosine of x. And that's precisely what we wanted to show. The derivative of sine of x is cosine of x. So we're done our proof. However, we have delayed two important, the verification of two important limits which are integral to our proof here. We've delayed these, and we'll do those on the next slide. So here is the limit we're going to spend most of our time working on. The limit as theta goes to 0 of sine of theta over theta is 1. Now there's a couple things I'm going to do with this limit. One, I'm going to give you a geometric way to look at this, which you can see the result almost immediately, just from the geometry. Then we're going to do a more rigorous verification that the limit is indeed 1 using the squeeze theorem. So that's going to involve the definition of the sine function and geometry and the fact that we use radian measure here, all of that's going to be embedded in this limit. So there's really a lot going on inside this limit, and we're going to want to unpack all of that. But first, for the geometric result. I think this is really useful just to see this, because once you see this the geometric rationale behind this limit being 1, it's one of these things that you probably will never forget. So what is the geometric picture here? So we're looking at sine of theta over theta. The first thing we should ask is, geometrically, what is sine of theta? And what is theta? Well, theta is the angle. Sine of theta is the y-coordinate of this point. It's the length of this line segment. What is theta? We've already said theta is the angle, but we're using radian measure. And this is the reason why we use radian measure in calculus, is precisely what's going on here. When we use radian measure for the angle theta, the length of this arc is exactly the value of the angle, the measure of the angle. So what's the length of the arc? The length of the arc is theta. What's the length of the red line? Length of the red line is sine theta. What's the length of the red line divided by the length of the arc? That's sine theta over theta. So this sine theta over theta is a ratio of the length of the red line over the length of the arc. Now, as theta goes to 0, because that's what we're interested in the limit, as theta goes to 0, how do those lengths compare to each other? Well, the arc, when we first look at it, we can probably think that, well, the arc looks to be a lot longer than the length of the red line segment. But when theta is small, the arc looks to be pretty close in length to the red line segment. So as theta shrinks, I'll zoom in here, as theta shrinks, what happens to the length of the arc and the length of the red line segment? They seem to be approaching each other. It almost looks like they're really one and the same. Now the arc, even though I've zoomed in a lot here, the arc is still curved. It's still slightly longer than the red line segment, but they are pretty close in length, and they're getting even closer in length the smaller the angle becomes. So if this is the length of the red line segment over the length of the arc, then their ratio should be going to 1. And that's exactly what this is saying here. The length of the line segment divided by the length of the arc, as the angle shrinks, those lengths go to each other, or the ratio goes to 1. Okay, so that's the geometric reason behind this. And now we shouldn't forget this, right? We've got this now mental picture, and we know geometrically what sine of theta and theta represent in the mental picture. And as theta is shrinking, these lengths of these line segment and the arc are going to each other, so the ratio is going to 1. Okay, so I'm going to prove this now rigorously. So we're going to call this maybe result 1, and I'll call this result 2 here, and we'll focus on the proof of result 1. Okay, so in mathematics, even though we've got some intuition being developed from the geometry, from that dynamic construction that I did, I move things around, I sort of see that things are doing what I expect them to do, and it suggests that the limit is 1. That's still not a rigorous argument that the limit actually is 1. We have to appeal to properties of limits that we've developed. And the properties of limits that we developed, we have a whole list of them, and one of them turns out to be quite useful, and that is the squeeze theorem that says if I want to know what the limit is of a function, if I can trap it between two functions I know what's going on with, then I can determine what the thing inside is doing. And that's what I'm going to do here. I'm going to, so we will show that this function sine theta over theta, it's trapped between 1 and cosine of theta. So that as theta goes to 0, what happens? As theta goes to 0, cosine of theta goes to 1. So this thing that sine of theta over theta is bigger than is going to 1, but it's also got to be smaller than 1. Then we would conclude then that the sine of theta over theta is trapped between 1 and 1, so has to be 1 in the limit. And that's by the squeeze theorem. So I'm saying sine of theta over theta is trapped between two functions, the constant function 1 and this smaller function cosine of theta. But as theta shrinks, sine of theta always has to be bigger than cosine of theta, which is going to 1. So sine of theta has to be trapped between 1 and 1, and so it's got to be 1. So by the squeeze theorem, we get the result. So that means we've reduced the argument to showing this inequality. And there's really two parts to this inequality here. There's that upper bound of 1, which I'll call inequality 1 here, and then this I'll call inequality 2. And we're going to verify these ones. So let's look at inequality 1. Inequality 1 says start with a picture here so we can get a relationship. Okay. So there's our point, our arbitrary point on the unit circle. What do we know about this point on the unit circle? Well, we know it's y-coordinate, and so if this is theta, we know the y-coordinate of that point. And if we're in quadrant 1 here, then that's just the length of that vertical line segment. So that's the sine of theta. I'm going to connect that point with this point down here by a straight line. That's supposed to be straight. And let's fill in a few things here. I'll call this maybe A, and this B, and this C. So we've got these points here. Now what do we have from this diagram? Well, we know that theta is what? Theta is the length of the arc from A to B. Why? Why is theta the length of the arc from A to B? This is the important part here about we're using radian measure. So really this is where it all boils down to. Why do we use radian measure in calculus? Because we want this equality right here. We want this equality right here to be true. Ultimately, it's really the point that why do we take radian measure? Because this limit turns out to be 1. The limit we're trying to verify is 1. It turns out that that limit is 1. If we don't use radian measure for the angle theta, then this limit turns out to be something else, something involving 360 and 2 pi, sort of this conversion between radian and degree measure that crops up there. So in some sense, we use radian measure to sort of normalize these results. Theta is the length of the arc. What is the length of the arc as compared to the length of the line segment AB? Well, the line segment AB is the shortest distance between 2 points is a straight line, so the arc has to be bigger than the line segment connecting the same 2 points. Now we've got a little right triangle here. I've got a hypotenuse. Hypotenuse is the longest length of all 3 sides of the triangle, right triangle, so it's got to be longer than CB. Oh, but what is CB? CB is the height of that point, which is its y-coordinate, sine of theta. So what we have is that theta is bigger than sine of theta, or in other words, sine theta over theta is smaller than 1. And so we've verified our first inequality. What about our second inequality? Again, we'll start with the same diagram. You might want to think about what we're using here in our argument. We're using a unit circle, and the fact that the sine function is the y-coordinate of the point on the unit circle corresponding to the angle theta. In other words, we're using the definition of the trig function sine and cosine and their relationship to the unit circle. That's what we're using here. And we're using the one additional fact that our angles are measured in radians because of the connection with the length of the arc. Okay. So we're going to do the same thing, only in this case I'm going to add a little bit more to the diagram. I'm going to add the vertical line here. I'm going to extend the radial line segment here. They're going to intersect at a point. I'll still call this point B and this point A. Now I'll call this point C, and I'll do a tangent line here. Call that D. The tangent line I've taken at B is perpendicular to the radial line segment, so there's really a right angle here. Okay, so I've added a little bit extra to the diagram. And the goal here is to add extra to the diagram so I can get some relationship between lengths and then hope the inequality that I'm looking for pops out. So what do we know? Well, we know again that theta is the length of the arc from A to B. What is the arc from A to B? Well, that arc is sort of cutting the corner. If I was to travel from B all the way to A by going from B to D and then from D to A, that arc is, in some sense, cutting that corner. So it's taking a shorter route. So this has to be smaller than B to D and then D to A. Okay, so now I look at that line segment BD. That's one of the legs of this right triangle that's sitting up on the top. One of the legs, not the hypotenuse, just one of the legs. It has to be shorter than the hypotenuse. The hypotenuse is the longest of the three legs. So this has to be, BD has to be shorter than CD. So CD. And then I still have that other line segment DA hanging on. So now I've got that theta is smaller than the length from C to D, then D to A. But C to D, the D to A is really just the line segment from C all the way to A. What is the line segment C all the way to A? Well, I have that angle theta. Should have drawn it in there. There's that angle theta. What's the distance here from that point there, O, all the way to A? Well, that's 1, because we're on a unit circle. I have a big right triangle here. One of the sides is 1. The other side is CA, and the angle is theta. What relationship do I have between the two sides of the right triangle and its angle? So the relationship I have is tangent. So this is tan theta. So we've got that theta is smaller than tan theta. So all of that work was just to get this identity that theta is smaller than tan theta. Well, what does that mean? Well, tan theta is sine theta over cos theta. So rearranging it a little bit, I get that sine theta over theta, so moving the theta to one side and the cosine to the other. Cosine is smaller than sine theta over theta. And so I've got that other identity. So I've verified those two identities. Or sorry, these two inequalities, I should say. I've verified these two inequalities. And then we've got the rest of the argument there that says, well, now you use the squeeze theorem and you get the result. So all our work was involved in trying to verify these two inequalities, and then we used the squeeze theorem to knock off the result. So we've now verified this limit of sine theta over theta, that it's actually 1. We've got a geometric way to look at it, the arc and that vertical line segment, and seeing how things sort of shrink and the lengths go to each other. So that should be ingrained mentally in your mind, so that whenever you look at this limit, you think of that, and you'll never forget the result. We've done the verification now that the limit is indeed 1, going back to first principles involving limits and all of the properties that we have associated with limits. Now we can take this limit, add it to our toolbox, and use it whenever we need to for this course and beyond. There's still this other one, this second limit that we needed in the calculations of the derivative of sine being cosine and using the definition of derivative. There's still that second limit that we need to verify. We don't have to go back and do an argument like we've done for the first one, because we can leverage off of that argument. You know, if I've proven something, I'm going to try to make use of it in future arguments. So I've just proven something about the sine function. I'm going to try to use it to prove something now about the cosine function. And here's the thing. Whenever I have a function involving cosine, I could probably try to always rewrite it in terms of sine functions, or vice versa, because I know that sine and cosine are related to each other. In fact, I know that sine squared plus cos squared is 1. So what I'm going to do here is I'm going to say, well, I'd really like there to be a sine up top. So I'm going to multiply cosine of h minus 1 by cosine of h plus 1. And if I do that to the top, I'm going to also have to do that to the bottom. Now, why did I multiply by cosine of h plus 1? Well, the reason is now when I multiply these things out, I get a cos squared. The cross terms cancel, cos of h minus cos of h, they cancel to give 0, minus 1 all over h times cos of h plus 1. So that thing on the top now, cosine squared of h minus 1, Well, I know that is exactly negative sine of h because of the trigonometric identity. Cos squared plus sine squared is 1. So this is negative sine squared h. That's all over h. And, oh, I've switched to h's here, and I left the limit in theta. I really should correct this. So I'm thinking in terms of h because of the definition of derivative and where these limits originally came from. But I think I wrote at the top of this page the original limit in theta, so that's why I'm getting the variables confused. This should be an h all the way down then. That's the quickest one to change. Okay, so this is cos of h plus 1. Now as h goes to 0, the bottom's going to 0 because of that h term. The top's going to 0 because of the sine h. But here's where I notice that, hey, wait a minute, that h in the bottom that's causing a lot of problems because it goes to 0, I can always pair it up with one of the sines in the top. And I know how to deal with sine of h over h because that was what I put all my effort into in the previous argument, working out that limit. So I'm going to leverage off all that work. There's still a sine h that's hanging on the top, and there's still a cos h plus 1 on the bottom. So now what happens as h goes to 0? This goes to 1, this goes to 0, and this bottom here goes to 2. So the whole thing is going to 0, because it's 0 divided by 2 times 1. And so there is our result. Okay, so the idea was to find the derivative of the sine function to show it's the cosine function. We used the definition of derivative. Two limits popped out. These two limits popped out. We needed to deal with those. I put a lot of effort into verifying that limit is 1, and then I used that to verify the second one was 0. The effort that was involved in verifying the first limit was 1 involved the definition of the function itself in its relationship to the unit circle. It also involved the idea that we are using radian measure and its connection between the angle and the arc length. So all of these things are coming up and they're all involved here. All of these things related to trigonometric functions are deeply behind the scenes here in this result. The derivative of sine is cosine. There's a lot going on behind the scenes here. But now that we've proven this is excellent. We've got this result. Now we throw it in our toolbox. We can use it whenever we want now. We don't have to go back and verify it every time we want to use it. We've now proven that the derivative of sine is cosine. We can use it whenever we want now. And in doing that proof, we got these pretty cool limits coming out as well. These are two extra things that we didn't expect to get at the beginning of all this. There are two extra limits that now are pretty special. We're going to throw those in our toolbox. So now we've got a number of things in our toolbox, derivatives and these two extra limits, all to do with trigonometric functions. So let's go ahead and apply these things that we've just learned. The derivative of sine is cosine, and the corresponding derivative of cosine is negative sine. Same argument works there, same limits come up. So you can spare having to compute the limits and then just do the same argument that we had for verifying the derivative of sine was cosine. You can do that same limit definition for cosine of sine. Now that we've got those things, we can do a bunch of examples.